whole career I've been looking at trying to understand and solve large-scale air pollution and climate problems. Air pollution causes about 4 to 7 million premature deaths per year worldwide, and about 20% of these are children under the age of 5 years old. And even in the United States, even though there's a lot of regulations that have helped in the last, 50 years, there's still about 65,000 deaths per year in California, around 13,000 premature deaths per year, and many of them in the Central Valley, Los Angeles area. And global warming, of course, is an increasing problem. It's already causing lots of damage. It's expected to cause $25 to $30 trillion per year of damage by 2050. And of course, fossil fuels, even if there weren't environmental problems associated with them, are limited resources. They will run out over time. Their cost will rise, so there will be social, economic, and political instability that will result. So these are all drastic problems that require immediate and drastic solutions. So our idea is pretty much to electrify or provide direct heat for everything and provide that electricity and heat with 100% clean renewable energy, namely wind and water and solar power. So just to give you examples, so for transportation, we would switch to battery electric vehicles, some hydrogen fuel cell for long distance truck, ships, and planes. Heating, cooling, we use pretty much heat pumps for most everything, including refrigeration, air heating, air conditioning, any type of heating or cooling, and some solar hot water preheating. In industry, we use electric arc furnaces, induction furnaces, dielectric heaters. These are all electric devices that exist. And we provide the electricity with just onshore and offshore wind power, concentrated solar power, photovoltaics on rooftops and in power plants, some geothermal power, tidal, some small amounts of tidal wave power, and existing hydroelectric power. So just to give you an example, I mean, things are happening so fast. I mean, there are already electric airplanes flying in the air. And here on the left is one, a small one. But it's expected that within 5 to 10 years, there will be commercial aircraft seating 50 to 100 people going 1,500 kilometers or less, just pure electric. And then we hope the rest will be hydrogen fuel cell electric hybrids. On the bottom right is an existing hydrogen fuel cell aircraft that seats 4 people, has a range of 1,500 kilometers. And on the top right is a drawing for a hydrogen airplane. I mean, first of all, hydrogen is an existing technology. Pretty much all rockets and the space shuttles have been lifted into space with hydrogen. So, but we want to use it in fuel cell. You need a larger fuselage, but hydrogen weighs less than jet fuel, so the overall drag is similar, even if you have a larger airplane. Anyway, as I mentioned, for industry, we use electric arc furnaces, dielectric heaters, induction furnaces. These are pictures of existing induction and arc furnaces. And the other thing that's really taken off a lot, or starting to take off, which will really open up the ability for massive wind power, even much greater than it is today, is floating offshore wind, which now exists at the commercial scale. Several countries are producing floating offshore wind turbines, such as on the left here. I mean, the oceans have such enormous wind potential, it's incredible. The east coast of the US could power the entire United States alone, electricity supply just with the offshore wind there. The west coast too, although the west coast is deeper, so it's much more expensive to put wind turbines that drill into the bottom of the ocean surface, bottom of the ocean, which currently most wind turbines do. So with the advent of these floating wind turbines, even the west coast offshore resources can now be used to power pretty much the whole west coast of the US and Canada as well. And then floating offshore solar is also growing. This is especially important for places that are constrained by land, island countries too. For example, Singapore would be one, Gibraltar is another place, but in Japan they're also using floating offshore wind, solar, and in China covering lakes with it as well. So wind and solar are just growing incredibly. I mean, in the first 2 months of 2018, 98% of all new electric power in the United States was wind and solar. And in the last 3 years, they were combined the largest source of new electric power ahead of natural gas. And the reason is because the costs have come down so significantly on the utility scale for onshore wind and for large-scale solar. It's just incredible. I'll mention that in a little bit. But the other thing we need, because the wind doesn't always blow, the sun doesn't always shine, is storage. And so we propose, well, for electricity storage, we use concentrated solar power, which has storage associated with it, pumped hydroelectric power, existing hydroelectric dams. We don't propose to grow the amount of hydroelectric power, just use existing hydro more efficiently. And batteries. Batteries are now coming down in costs, so are becoming competitive with these other storage options. For heating and cooling storage, just water tanks, ice, or rocks underground. Really cheap existing technologies, and I'll show you some examples in a second. Hydrogen is also a form of storage. Just basically, when you have too much wind or solar, you can use it to produce hydrogen that can be stored in a tank, and then that can be used for transportation. And another way to help match power demand with supply is by what's called demand response, where utilities will give people incentives to use electricity at certain times of the day and not at other times. For example, the cost of electricity between 11 p.m. and 7 a.m. PG&E's cost of electricity is around 11 cents a kilowatt hour, but if you go to the peak time of the day, it's like 45 cents a kilowatt hour. So using your electricity to charge your electric car or to run your dryer or washer between 11 p.m. and 7 a.m. obviously makes economic sense if you want to save some money. So that's demand response. To give you an idea of some of the existing storage technologies that have been used for a long time, this is ice storage. So Stanford University has had an ice cube under a building since 1998, well, until a couple of years ago. And at night, when electricity price was low, the electricity was used to produce the ice. And then during the day, instead of running air conditioning at peak times of the day, where the cost of electricity is high, water was just run through coils in the ice, and then the water was sent to buildings to cool the buildings. So this is used actually on a large scale in stadiums and big neighborhood complexes, the hospitals. So this is an existing technology, but it costs around $30 to $40 per kilowatt hour of storage, which doesn't mean anything unless you compare it to something. So batteries are between $200 and $300 per kilowatt hour of storage. So it's like 1/10 the cost of batteries for this ice storage, but it does the same thing. It avoids electricity use in the afternoon, which is what a battery would do. And this is a community in Okotoks, Canada, 1 hour south of Calgary. In 2005, there were 52 homes that were built, and there were solar collectors put on the garages, and you can see on the top left, the solar collectors. And these solar collectors had a glycol solution in them. And so in the summer, when you have long days, that glycol solution would absorb the sun's heat, and then the solution was piped to this building on the right, where the heat was transferred to water. The water was then piped under this field, which had been excavated and filled with rocks, and then covered up. And the rocks are heated in the summer up to 80 degrees Celsius, and the rocks are insulated, and the heat is stored until wintertime when snow is on the ground, like on the bottom left, and the whole system is run in reverse, and that heat is used to power 100% of the wintertime heat for these 52 homes. And that costs less than $1 a kilowatt hour of storage, compared to $200 to $300 per batteries. So this is called seasonal heat storage. It's a form of district heating, and in Europe, district heating is very common, except not with these rocks, but usually they use water tanks instead for short term, like on the order of a week storage. Anyway, the point is there are many storage options for heating and cooling and even electricity, and many of these options are low-cost storage. So the batteries are probably the most expensive type of storage there is, compared to everything else. But when it turns out when you electrify everything or provide direct heat and then use wind and water and solar to power that electricity or heat, it actually makes the whole trying to match power demand on the grid much easier. It's a much easier problem when everything is electric, because there are more flexible loads, meaning like a light switch is not a flexible load. You have to have the power instantaneously when you turn on the lights. But an electric car is a flexible load. because you don't have a plug plugged into the car while you're driving. You have batteries to store the electricity, so you can charge those batteries any time of day or night. So the more things that you have where you have some kind of flexibility, such as water, storage in ice, storage in batteries, then it's a lot easier to solve the problem. And it turns out it's easier when you electrify everything than if you have the current energy system, where electricity is only 20% of all end-use energy worldwide. I mean, we often think of energy in terms of electricity, but that's only 20% of the energy. Most of the energy is in transportation, industry, heating, and so when you electrify all those sectors, then the problem, you not only reduce your power demand significantly, but this problem becomes easier. One more example of storage. Stanford actually had a big natural gas cogeneration plant that would provide 80% of the electricity and heat for the university right outside my office. And a couple years ago, it was bulldozed and replaced with these 2 boilers and a chiller and 50 megawatts of storage down in the Mojave Desert. Sorry, 50 megawatts of solar, 50 megawatts of solar photovoltaics that they installed in the Mojave Desert. So what these are, the 2 boilers and a chiller, and what they determined was, well, at any time of the year, the university needs both hot and cold somewhere in the university. So on the right, there's a diagram from January to December showing the cold demand in blue and the heat demand in red. And so there's greater heat demand in the winter, January, December, and greater cold demand in July and August. And in any case, whenever you produce heat, you release cold, and when you produce cold, you release heat. So instead of wasting that heat or cold, it's captured, it's sent to these tanks, these cold tanks, or hot water tanks and cold tanks, and stored, and then shipped around the university with an elaborate piping system. So that reduced energy demand significantly, and then the remaining electricity needed for up to 80% is generated by solar. So this is another way. You don't need gas at all to solve this problem. You don't need natural gas. I mean, they just took the gas plant out and the grid's running fine on the Stanford campus. So let me just go down to an even finer scale. I built a new home last year, and my goal was not to have any gas on the property, just run it all on electricity. So I just want to show you what I did, because after 1 year, everything's working perfectly fine. So for water heating, I have an air source heat pump water heater. And what a heat pump does, a heat pump, by the way, it uses 1/4 the energy as either an electric resistance heater or a gas heater. Because it doesn't create heat, it moves heat. It takes heat, in this case, it takes heat out of the room, it's in a mechanical room, it takes heat out of the room and moves it to the water in the tank. And then it expels cold. So the room becomes a little cooler, but the water becomes warm, just like your gas water heater or electric resistance water heater. But it uses 1/4 the energy, so your energy just plummets. And on the right, the house is heated and cooled with what's called, these are also air source heat pumps, but they're called ductless mini-split air source heat pumps for they're also air conditioners as well as heaters. So there are no ducts. So often you'll have like a central heating system and a duct system where you send the heat through the house. These big ducts, they have a lot of losses. But here there are no ducts. They're just copper pipes between like this unit, which is on the ceiling, and an outside unit, which exchanges heat with the outside air. And there's a copper pipe. So what happens is, when, let's say it's hot in the room and you want to run air conditioning, you want to cool down the room, the heat just blows through this unit and blows over the copper pipes, which have coolant in them. And the coolant absorbs the heat and sends out cold air to the remaining air, which is cold now, to the room. And that heat goes into the coolant and is then sent through the copper pipe to the outside, where it's expelled to the air outside. So it's moving the heat from the inside to the outside. It's not creating heat. So this uses 1/4 the energy as any type of gas heater with ducts or ductless, or an electric resistance heater. And same thing with air. If you want to warm the room, you do the same thing. You run the air over the coolant, then you'll take out, the coolant will absorb the cold, and you'll release heat to the room, and then the cold is expelled outside. So this can also, you can also run this with what's called a ground source heat pump, where you extract the heat out of the ground or from the water. There'll be a water source heat pump. Anyway, it's really efficient. For stoves, most people don't like electric stoves because they don't heat up very fast, you can't control the heat very well so much as a gas stove. But not with it. This is an electric induction cooktop stove, which boils water in half the time as a gas stove does, and then it doesn't feel hot when you touch it. And so, and you do need special pots that have either iron or stainless steel bottoms. But you know, I bought 12 pots for $350, so it's not just like any other pots you would buy. But the reason it doesn't feel hot is because while you have it, when you have a gas burner, you're burning, you have something burning on the stove, and then that's heating the pot. In this case, what's going on is it's exciting molecules in the iron on the pot. So the pot itself, because the iron is creating resistance, the pot itself heats up. So the stove does not heat up, but the pot heats up. And so when you take off the pot from the stove, you can touch the stove and it won't feel hot. It's just the pot that it's on. In any case, it cooks just as well, and it doesn't cost any more than a regular stove. So the powering for the roof, or for the energy in the home, it's all powered by sunlight. There's solar collectors on the roof, and there are batteries in the garage. And I have 4 batteries, and although PG&E only allowed me to turn on 2, but it turns out that's okay because I only needed 2. If I actually turned on the other 2, I'd actually lose money because I'd be powering the batteries at a higher cost than I'd be using them at. So it turned out 2 is perfectly fine. I can just use the other 2 in an emergency, like when all the power goes out of the neighborhood, or when the first 2 run out, then I can use the other 2. But, so everything is powered by these batteries and the solar, including electric cars. And the electric cars turn out to be what takes the most electricity in the house. But let me just give you an idea of how many people can read it. I'll try to explain. This is like 1 week of usage of this in this house in the summertime. The green is the production of solar electricity from solar PV. The light blue during the day is the use of electricity from photovoltaics. The dark blue is the use from batteries. So what happens is, the first thing that happens in the morning, the solar powers anything that you need in the house. Once that's satisfied, then it fills up the battery. So the battery gets filled every morning after the house electricity is satisfied. Then during the day, though, the battery's not used because the solar is used. Only at night, when the sun goes down, does the battery kick in and start providing the remaining electricity used for the house. And only when the battery runs out does the grid come in. The grid electricity is in the red here. And that really only came in this week when I was charging the cars. One car required 20 kilowatts charge rate, the other was about 10 kilowatts. And that was, the batteries are only a total of 6.6 kilowatts. 2 of them are fed. All 4 batteries would have been 13.2 kilowatts. But anyway, so despite using some grid electricity, it turned out that even during this whole week, I actually sent 50% of my solar back to the grid. And now, most communities, including this community, can use what's called a community choice utilities. In this case, it would be Silicon Valley Clean Energy. So PG&E is the underlying utility that you're running your transmission and distribution lines, and they can also provide your power. But now you have an option of going to a community choice utility that you can actually choose to go to 100% renewable energy with that utility. So in the peninsula, there's one in the peninsula, there's one in Silicon Valley. But in this case, I'm actually producing more power than I'm using, and because with this community choice utility, they will actually pay much more than PG&E. When you overproduce over a year, during the year, if I overproduce and sent the electricity back to PG&E, they would only pay 2 cents a kilowatt hour for the excess, regardless of what time of the day that you produce that electricity. But with the community choice now, they will pay you at time of use for the generation portion, which is up to 25 cents a kilowatt hour. So that's like 12 and a half times more than PG&E is paying for extra electricity. So for this past year, for example, I generated about 20% more electricity than I used, and I'll get a check for around $700 or $800 within a couple weeks, which PG&E would be like about a $30 check. So anyway, this is good news because these community choices are now everywhere, or lots of places, especially in California. And you can actually option, if you want 100% clean energy, you can actually get it from these, and it's about the same cost, literally within 0.008 cents a kilowatt hour of PG&E's rates for 100% clean energy. They will guarantee that your energy is coming from wind or solar or geothermal or hydroelectric power. So this is good news for those of you who are interested in that. Okay, so now let me just move on to, can we actually power the whole world with just clean renewable energy? So we developed roadmaps for 139 countries of the world for which data were available, and the ones that weren't included were mostly small island countries and a few countries in Africa that we didn't have data for. But just to summarize, the end-use power demand in 2012 in all these countries was about 12.1 trillion watts or terawatts. It's expected to go up to 20.6 terawatts in 2050. But if we electrify everything, provide that electricity with wind and water, solar, interesting thing happens. The power demand can go down by up to 58% without changing your habits. It's simply because electricity, 23 percentage points of that is because electricity is more efficient than combustion. For example, an electric car, 80 to 86% of the electricity going into the car goes to move the car, and the rest is waste heat. For a gasoline car, only 17 to 20% of the energy in your gasoline goes to move your car. The rest is just heat that's expelled to the car and to the air around you. So you actually reduce power demand with an electric car by a factor of 4 to 5. But averaged over all energy sectors, there's about a 23% efficiency improvement due to electrification. Then you get another 13% energy reduction due to the fact that that's how much energy is used to mine, transport, and refine fossil fuels worldwide in uranium. So you eliminate that energy right there because when you have a wind turbine or solar panel, the wind comes right to the turbine, the solar comes right to the panel, you don't need to go dig it up. And then with heat pumps, while one heat pump will reduce your power demand for electricity, for energy, by 75%, heating is only a certain portion of total energy, so when you average over all energy sectors, you can get about a 16% reduction in power demand if you used heat pumps for everything worldwide. And then another 7% reduction due to end-use energy efficiency improvements beyond business as usual. So we could get from 20.6 terawatts to 8.6 terawatts of energy demand just by electrifying everything, getting rid of gasoline, diesel cars, and trucks, buses, electrifying everything, and powering that with clean renewable energy. Now the next things I want to show though are with the 11.8 terawatt number, which is without heat pumps, just because we did some analysis before we added heat pumps, and so I'll show you that. So this is how many devices you would need to power the entire world, basically, because the 139 countries represent 99% plus of all emissions worldwide. To get to 11.8 terawatts, this is the number of wind turbines and solar panels you would need worldwide. And so it would be about 23.5% onshore wind, 13.6% offshore wind, 60% residential rooftop PV, 12% commercial government rooftop PV, about 20% PV power plants, 10% CSP power plants, 1% geothermal, 4% hydro, and a small amount of tidal wave. And on the right is the number of devices. There's no new hydro, that's why there's a 0 there. We just use existing hydro, and that's actually, the existing hydro represents 4% of all the energy we would need in 2050. And so we need about 2.5 million wind turbines. But that may sound like a lot, but think about it. I mean, in the United States alone, there are 1.7 million active oil and gas wells alone. This is worldwide. and 2.3 million inactive wells. So in the US, there are 4 million active plus inactive oil and gas wells that take up 1 to 2% of the land area of the entire United States. So compare that to just 2.5 million wind turbines worldwide. So anyway, the land area required for this whole thing is about 1.1% of the world's land, and most of that is spacing between wind turbines. So the land, you can see there's zero new hydro, that doesn't take up new land. Rooftop solar doesn't take up any new land. Geothermal hardly, it's only utility PV and CSP, which takes up about 0.22% of the world's land. And then the onshore wind, which is about 0.9% of the world's land, but you can use that for open space, farmland, rangeland, cropland, or open space. So that, anyways, 1.1% is, compared to other land uses, it's pretty minor, and this would be to solve all the energy problems worldwide. We did a case, well, I only have 5 minutes, I'm going to just be really brief. We looked at grid stability throughout the world in 20 world regions with 3 different scenarios, A, B, and C. One was with batteries, concentrated solar power storage, heated cold storage with no heat pumps, no additional hydropower turbines, with pumped hydro storage, and with hydrogen for transportation. That was one case. Then another case was the same, except no batteries, but we increased hydropower turbines on existing dams. And the third case was the same as the first case, except no hot or cold storage. We used heat pumps instead, and that was pretty much the same difference. But in all cases, the cost of energy worldwide was about the same. We were able to keep the grid stable everywhere. But notice the demand reduction was between 42 to 58% because of the use of electricity and wind, water, solar. So I just want to show you some results for these 20 world regions really fast to keep the grid stable. We looked over 5 years. We ran simulations every 30 seconds for 5 years using predicted winds every 30 seconds, predicted solar radiation fields, and compare those with demand. And we also included all the storage options I talked about. So this shows 30 days of simulation. The blue, well, the red is energy supply. The blue is demand plus changes in storage plus losses plus shedding of energy. And what it shows is that the supply is matching the demand. This shows every hour. It's matching the demand exactly. And this is for North America, US and Canada. This is for Central America, Cuba, Haiti, Dominican Republic, so it works for islands, Jamaica, South America, New Zealand, Australia, Southeast Asia, Philippines, Japan, South Korea, Taiwan, China, Hong Kong, Mongolia, North Korea, Russia, Georgia, India, Nepal, Sri Lanka, Central Asia, Middle East, Europe, Iceland, and Africa. So the entire world, we're able to keep stable at low cost. The cost of energy, well, the fossil fuel cost of energy in the electric power sector is about 9.8 cents a kilowatt hour. The health cost is 12.7 cents a kilowatt hour for air pollution. The climate cost is about 15.8 cents a kilowatt hour. Total, 38 cents a kilowatt hour is the social cost of energy from fossil fuels. That compares with our wind, water, solar, 9.7 cents a kilowatt hour, almost the same as the direct energy cost of fossil fuels, but there are no health and climate costs. So we have 1/4 the cost of energy per unit energy, but we have 50% less energy. So the consumer pays 1/8 that the consumer does in the current system. Because if you account for the social cost, the health and climate cost, and the fact that you reduce your energy use, that's 1/8 that people are paying in society for wind, water, solar. Let me skip this and skip this. Just a couple things about, okay, what have we done with these energy plans? Well, first of all, do people want this? There was a survey a few months ago, 13 countries, 26,000 people, it's a pretty large survey. 82% of the world wants 100% clean renewable energy, according to this survey. Only 66% of the people believe climate change is a serious problem. So why do so many more people want 100% clean renewable energy than believe climate change is a serious problem? Well, it's because there are reasons people like clean energy, some of it's because it makes countries energy independent. Another reason was it boosts economic growth. 73% say renewables will boost economic growth. So there are a variety. You can believe, in other words, in renewable energy without having to believe in climate change. I'm not trying to say you should believe in climate change. You definitely should. But from our point of view, we're trying to solve the problem. Maybe it doesn't really matter if you believe it or not. Right? Who believes it? All we really want to do is solve the problem and solve a lot of other problems simultaneously. Here's another poll that was very consistent. This is a poll just in the United States for seven states, including New York, California, North Carolina, Colorado, Maryland, Virginia, and Iowa. Nationwide, 64% strongly supported 100% clean renewable energy, 19% somewhat supported, so that's 83% want either strongly or somewhat support 100% clean renewable energy. That's very consistent with the previous poll. Only 16% are against it. There are actually 4 laws laws or resolutions pending in Congress for the United States to go to 100% clean renewable energy. There's House Resolution 540, Senate Resolution 632, Senate Bill S987, and House Bill 3314 that all call for the U.S. to go to 100%. And we've developed plans for the last 9 years now, and we're actually seeing some results. New York now has a 50% law. California has a 50% law as well for electric power, and has a 100% law being proposed, SB 100. It's supposed to be voted on, but we'll see. Washington State has a 100% carbon-free electricity law being proposed. Hawaii already has a law in the books to go to 100% renewable electricity by 2045. Massachusetts has a law proposed to go to 100% in all energy sectors by 2050. There's over 60 cities that have committed, in the United States alone, that have committed to 100% clean renewable energy, including large ones such as Atlanta, Georgia, St. Louis, Missouri, Madison, Wisconsin, Portland, Oregon, but also in San Francisco and Palo Alto too. But there are also small cities, like we have 14 towns and cities in North Carolina alone that have committed to 100% clean renewable energy. There are over 130 companies, international companies, that have committed to 100% clean renewable energy, including Apple and Google have actually reached those goals, according to what they've said. Actually, Google did it all of 2017. They said they went to 100% for their electric power, and Apple's a few weeks ago announced it. But there are 130 companies, including all the major companies of the world, that have now committed to this. And finally, there are over 70 nonprofits that have committed to 100% clean renewable energy. And so this has really helped to get the information out. So just to summarize, if we do this transition worldwide, we can create over 24 million net jobs over lost long-term full-time jobs. In the U.S., it would be about 2 million more. We require around 1.15% of the world's land for footprint or spacing. We'd avoid 4 to 7 million air pollution deaths per year. We can slow and reverse global warming. We can keep the grid stable with 100% renewable energy. And the cost of energy will be less, especially to the consumers, because you're actually using less energy. Transitioning is technically and economically possible. The main barriers are social and political. The solution does require collective willpower, but immediate deployment. And then finally, if you're interested, here's some websites, or if websites where a talk similar to this is posted. There are also papers behind all these, everything I showed you. And you can go to the solutionsproject.org for actually simple infographic maps of states and country roadmaps to 100%. And also, if you want more information up to date, really quickly, I post a lot of stuff on Twitter. So thank you very much.
Thank you. For the sake of time, I think we've got a lot of questions. If you have a couple minutes, stay behind.